Section 15.1, the concept of equilibrium. Let's examine a simple reaction to see how it reaches an equilibrium state, a mixture of reactants and products whose concentrations no longer change with time. We begin with dinitrogen tetroxide, a colorless substance that dissociates to form nitrogen dioxide, which is brown. Figure 15.1 shows a sample of frozen dinitrogen tetroxide inside a sealed tube resting in a beaker. Because the chemical reaction occurs in a closed system, the reaction will eventually reach equilibrium. The solid dinitrogen tetroxide vaporizes as it is warmed above its boiling point at about 21.2 degrees Celsius, and the gas turns progressively darker as the colorless dinitrogen tetroxide gas dissociates into brown nitrogen dioxide gas. Eventually, even though there is still some dinitrogen tetroxide in the tube, the color stops getting darker because the system reaches equilibrium. We're left with an equilibrium mixture of dinitrogen tetroxide and nitrogen dioxide in which the concentrations of the gases no longer change as time passes. The equilibrium mixture results because the reaction is reversible. Dinitrogen tetroxide can react to form nitrogen dioxide, and nitrogen dioxide can react to form dinitrogen tetroxide. The situation is represented by writing an equation for the reactions with two half arrows pointing in both directions. We can analyze this equilibrium using our knowledge of kinetics. Let's call the decomposition of dinitrogen tetroxide to form nitrogen dioxide the forward reaction, and the reaction of nitrogen dioxide to reform dinitrogen tetroxide the reverse reaction. In this case, both the forward reaction and the reverse reaction are elementary reactions. As we learned in section 14.6, the rate laws for elementary reactions can be written from their chemical equations. The forward reaction of dinitrogen tetroxide going to 2 moles of nitrogen dioxide, the rate law is K sub forward times the concentration of N2O4. The reverse reaction of 2 moles of NO2 gas going to 1 mole of N2O4 gas, the rate law is K sub R, or reverse K, times the concentration of nitrogen dioxide squared, where Kf and Kr are the rate constants for the forward and reverse reactions respectively. At equilibrium, the rate at which the products are produced from the reactants equals the rate which reactants are produced from the products. K sub F in the forward direction equals K sub R NO2 squared in the reverse reaction. Rearranging this equation gives you a constant, K sub F over K sub R. As shown in equation 15.5, the quotient of two constants, such as K sub F and K sub R, is itself a constant. Thus, the equilibrium ratio of the concentration terms involving N2O4 and NO2 equals a constant. We'll consider this constant called the equilibrium constant in section 15.2. It makes no difference whether we start with N2O4 or with NO2, or even some mixture of the two. At equilibrium, the ratio equals the specific value. Thus, there's an important constraint on the proper proportions of N2O4 and NO2 at equilibrium. Once equilibrium is established, the concentrations of dinitrogen tetroxide and nitrogen dioxide no longer change, as shown in figure 15.2a. If the composition of the equilibrium mixture remains constant with time, it does not mean, however, that dinitrogen tetroxide and nitrogen dioxide stop reacting. On the contrary, the equilibrium is dynamic. Some N2O4 is still converting to NO2, and some NO2 is still converting into N2O4. At equilibrium, however, the two processes occur at the same rate, as shown in figure 15.2b. We learned several important lessons about equilibrium from this example. At equilibrium, the concentrations of reactants and products no longer change with time. For equilibrium to occur, neither reactants nor products can escape from the system, and at equilibrium, a particular ratio of concentration terms equals a constant. We'll examine the last of these facts in the next section.